Hello and welcome at the working group of energy policy of the German Pirate Party. Today we have a special guest. We have Dr. Adrian Malko here. He is the CEO of Optec BB, the cluster of optics and photonics in the Berlin-Brandenburg region. And he's going to tell us something today about how to reduce the energy requirements for data centers by optics and photonics. Ariane, the stage is yours.
Thank you very much. Also, thank you for the invitation. And yeah, within the next minutes, I'll try to give first an overview, what's going on, what means internet and how much energy is consumed there, and how we overcome one or more of these bottlenecks in energy consumption to reduce our footprint on the planet based on just information and sharing informations. But first, before I go in detail, just give me some minutes, some words. Why do I'm talking about this? Yes, I'm scientist for more than 25 years. I also leading a research institute and was also part of another photonic sustainability revolution. But now I'm leading the Optec BB. And Optec BB is an association of companies and research institutes in the area of Berlin and Brandenburg. In this area, we have nearly 400 companies, 10 universities, and also 26 non-university research centers, which are working deeply in photonics. Some of them also leading on a global scale the research in their special manner. 1/3 of these entities are member of Optec BB, so we are a huge association in photonics. It's a huge association, and also we kindly responsible for these 24,000 employees which are working in this area in the field of optics and photonics. On an international scale, we also have a huge overview over the international scale and the international market, because most of my companies are exporting to the rest of the world. So 70, some 80% export rate, and also a huge amount of the money goes back in research and development to be at the edge of what is possible. There are a lot of hidden champions, small companies with just 10 or 20 people working in this company, but they are global leader in their little market. First, a very brief impression about the power within this area. And now I see also the conversation to PDF is also not working very properly. But nevertheless, maybe some of you heard about the change in the global system of units. So the kilograms and mole and candela and meter and second and so on. And with May the 20th, 2019, there was a historical change. For the first time in human history, all these units are not belonging to something which I can touch. They all belong to natural constants. So for the first time, the whole system of unit is fixed, and maybe forever. When these constants are really natural constants, then the system of unit is fixed. And the last missing link to this was the kilogram. The kilogram, more than 100 years, 150 years, was a little block made of platinum iridium, which was stored in Paris. And every 3 years, all the national institutes came with their kilogram and compared it to this with this standard. And there was always a mismatch. And now, from 2019 on, for the first time, the kilogram is based on the number of atoms. And to measure the number of atoms in 1 kilogram, there was a sphere made of 28 silicon, so isotopic clean silicon. And this silicon normally is also the fundamental for microelectronics. There was a single crystal grown in Berlin at the Institute of Crystal Growth. And then of these single crystal, 3 balls are cut out, goes to the other side of the planet, to Australia, to be polished. And then they came back to a small company called Zentech in Berlin to have a single atom layer of silicon oxide that we can touch it but not destroy it anymore. And then also in Berlin, the PTB, the Physikalisch-Technische Bundesanstalt, run their own synchrotron, and they count the number of atoms. And with this, we have the number of atoms in 1 kilogram. Now these spheres are not needed anymore. But with a little proud, you can say the new kilogram is made in Berlin. And these 3 entities and several over this are included in this research or in this development. But this has nothing to do with the internet. It's just a highlight from Berlin we're a little bit proud of. But now, let's jump in. We're talking about sustainability, and I will have always problems with this word. And we want to concentrate the aspect, the sustainability on the internet. First, I would give my idea, and not my, this is from also Wikipedia, but it's from Columbia Institute, and this is one definition of sustainability. It's the ability to meet needs, but this is the main point, without compromising the future generation. And so if we use something, we should reuse it. If we use energy, we should use as less energy as possible. And over global, it would be very nice to generate all these goods and all this energy without changing the environmental, and to do everything in balance. This is an ideal, but for the future generations, we have to meet as much as possible to this ideal picture. And in this talk, I will concentrate on one example, the internet. Just briefly introduction, what is the internet? It's a communication network between computers, so in general. Invented or started in 1969. The DARPA, a military organization in US, they have the idea they needed communication between computers for not relying on telephone or telegraph anymore. And they started with some computers, and they connect them via cable, standard cable, with 9.6 kilobit per second. After some years, more and more computers are connected to this network. The name Internet not yet born. But even in 1988, it appears that we need more standardized and more secured connections to this internet. And so CERT was born to start a process of trust. And also now ISDN, based on cable, 56 kilobit per second was the standard of the internet. One extremely important step now was 1991, when at CERN scientists set up a new language which gives us which transfers the communication via zeros and ones to something which is right now today I would say it's clickable, to include pictures, to make it more visible for the users. And even 30 years later, we are just at the speed of roughly 45 megabit per second. This was standard communication link within the internet. And 2005, back to sustainability. In this year, for the first time, the energy consumption of this structure, internet, little data centers, and also end users with their PCs or with their computers. For the first time at 2005, the energy consumption of the internet was higher than the energy consumption of lighting, of all this lighting on a global scale. And then a lot of new development appears, but in respect to energy consumption, I think the most important jump in the internet is now 2022, when ChatGPT goes public after 3 years of invention. But from this on, we have artificial intelligence, and everyone is using it, more or less property, but it's using it, and the energy consumption of the whole internet gets another jump, a really important jump. So that today we have to think about how to limit the energy of the consumption of the internet without limiting the communication, for example, or the bandwidth or something like this. So in general, the energy consumption of the whole internet was a point for the last 30 years, but nowadays it grows much faster. The energy consumption itself grows much faster than the energy production. And so we have to do something. Most of these pictures, some of these pictures or these graphics are for illustration. And as you can see, starting with maybe 3 computers, maybe we can call it a network, over some years between 100, 200 computers. But starting with 1991 with the www from CERN, the number of hosts in the internet explodes more or less. And nowadays there is kind of saturation. So we have some giga hosts in the internet, but now it's saturated more or less because the data centers get bigger and bigger, and not every consumer at the end of the internet is a host. When we go on, the internet, it's a network. It's based on communication links between computers. When it starts, 1969, we have 1.2 kilometers of BNC, so copper-based cable. And it was more or less difficulty to run the internet, and it based on cables until 1989. In this year, so it's more than 30 years ago, the first link between Europe and US was set up with a fiber. 3,600 kilometers of optical fiber in the Atlantic Ocean. This was the birth of optical communication in the internet. And 2 points. First, the energy consumption of such a cable between Europe and US was limited, because it runs with kilowatts of energy consumption just to have some megabit communication link between these 2 continents. And with optical fibers, there was a jump in the ability of communication. Nowadays, so in 2026, as more or less the whole internet based on optical fibers. There's no more copper or electrical driven long range link in the internet today. And in Germany, we have some 76,000 kilometers of optical fibers all over the country. And worldwide, what you can see here on the map, we have 1.8 million kilometers of sea cables. And each of these sea cable is not only one fiber, it's a bunch of 100, 120 up to 200 fibers. And all fibers worldwide, this is not a roughly estimation, but it's I counted a lot and calculated a lot. So it's roughly some billion kilometers of fibers worldwide. And just for comparison, it's also possible with all these fibers we have a link, an optical link between Earth and Uranus. So it's a really long distance. And on these, the whole internet based, and it's all optics. So already there was a revolution using photonics for the internet. And right now, the whole communication in the internet, so 99 plus 999% of the whole communication over long distances is run by fibers, by optical fibers. So this first revolution is okay, it's there. And also the speed and the bandwidth of all these fibers is increasing during the last years with new technology, but only at the end and the beginning of the fiber. The old fibers, 20, 30 years old, no problem. You can just change the transceiver at the beginning and the receiver at the end of the fiber to increase the bandwidth. You don't have to change the fiber itself. And this is also part of this optical revolution for this communication network. And the communication bandwidth is increased by more than a factor of 1,000. At the beginning, some gigabit per second over one fiber, and now standard communication links over one fiber is in the region of 400 gigabits, so a factor of 100 more. And the latest results in the labs, in the laboratory, show some I think the world record is 366 terabit per second, so another factor 1,000 higher than a standard datacom link right now or nowadays. So there's a lot of potential to increase also the speed over the given network of fibers. And this is also a very important point. The speed over a copper cable, standard cable, electrical driven, is just limited. And with light and different light and better lasers and so on, we can use given cables and increase the bandwidth dramatically. And this is also needed. This was something also for me not believable, but I have no idea about this huge amount of data. So this is the estimate, not the estimation. This is the calculation of all the transferred data in the internet. So long-term communication from data center to data center, from city to city or countries to countries, all over the world. And just for clarification, 1 byte, 8-bit, I think I don't have to explain this. But when we go further and further to higher and higher amounts, nowadays the data consumption or the data communication amount in the internet is counted in zettabyte, or zettabyte, sorry, zettabyte. And in 2024, some 173 zettabyte. So zettabyte is 1 billion terabyte, and 1 terabyte is 1 billion byte. So it's a billion byte. One, or in this case, a 173 with 21 zeros following. It's a huge amount of data. But calculating with this, I start with this number. This is a growing number. Also, the data consumption is growing yearly by 20% or something like this. Also for prediction, not bad. And with this, how much energy does the internet consume? This is the first question. Also to have an idea, is it even needed to talk about shrinking down the energy consumption of the internet? Maybe yes, I think so. When we go to the energy consumption itself, so in 2026, I calculate all these numbers to this year, we have some 184 petawatt hours of primary energy consumption. Primary means heating, electricity, gas, everything. Also the energy consumption in the industry to produce something which is completely different driven, oil, solar, coal, whatever. This is the whole energy consumption in 2026 of humankind. Only a smaller part of this is current or electricity. So round about, I just meant Strom, sorry, electricity. So it's 22 petawatt hours of energy consumption with electric power. And a not small amount of this is consumed by the internet. It's round about 3.8% of the whole electric power is consumed for the internet to run data centers, to run the communication between them, to run all the other needed infrastructure like 4G, 5G, mobile, and so on, but also to run the end users' machines, the PCs and mobiles and so on. This means we are talking about 812 terawatt hours of energy consumption for the internet. When we completely stop the internet, we will save 1/5 of our energy consumption on this planet. But we don't want this, I guess. So we have to talk about how to reduce the energy consumption of all these infrastructure. And the biggest part of the whole energy consumption are the data centers. In these data centers, we have some 1,000 worldwide, so the bigger ones. I only count the data centers which have more than 100 kilowatt of energy consumption. And there are some data centers with some 120 to 150 megawatts. So it's a huge, huge factory producing data. And the whole energy consumption of all these data centers is in the region of 650 terawatt hours per year. So most of the energy is consumed in the data centers. The rest, so as I mentioned, the communication between the data centers is run all optics. That's fine. So we can raise up the speed, but to go down in energy consumption, it's possible, but we're only talking about some percentage of the smaller part of the whole internet energy consumption. So the main energy consumption is in the data centers. And this is right now starting point for a right now ongoing revolution to run everything in the internet with photonics, so optics. Communication, I would say check mark. That's fine. The whole communication is done, all optics, and there is some potential to reduce the energy consumption, but not this much. But in the data center, there is a huge potential for energy consumption. And this is I want to point out now. To do this, I have no available data on a global scale. So we are Berlin-Brandenburg Association, and so we also have data from Berlin and Brandenburg about this. And so I use these available data just to calculate the potential of using latest developments in optics and photonics to reduce the amount of energy consumption for the internet. And then to calculate this with the example of Berlin capital region, we can also scale it up to a global scale. In Berlin, it's also not so bad to start here in Berlin, where I'm sitting, because also there's a lot of know-how and a lot of goods which are delivered to run the internet. First, we have around about 70 tier 2 to tier 4 data centers in the capital region, and also there are some big ones. So scale-up technology with some 40 and 20 megawatt machines, and also Google set up a huge, they run a data center with 35 megawatts, and they right now building a new one with 140 megawatts. So one of the biggest data centers in the world appears in this region. On the other hand, I mentioned the communication is done optically between the data centers. And there we have very, very good data because we here in this region, we build these transceivers and receivers. We don't build fibers. But as I mentioned, fibers are always there, but transceivers and receivers are built in town. So we have these companies, Coherent, SHF, and Sequoia, mentioned there with their logos. And these three companies together, they have a market share, a global market share in transceivers and receivers of around about 48%. So nearly half of all transceivers and receivers which are used worldwide in the internet to run the communication is built in Berlin. And right now, state of the art are 40 gigabit per second transceivers and receivers, and also the next generation and the generation after this, up to 1.6 terabit per second, is right now in the labs, also in Berlin, for example, at the HHI Fraunhofer. Mentioned HHI, this is a worldwide very well-known research institute on communication, optical communication, but also on data transfer. Maybe you know the video compressing standard, the H.264, which is all streaming services are working with the standard. And this is invented by HHI, for example, so several years ago. And half of the traffic in the internet, roughly, is streaming. And so half of the communication in the internet works with in standard and pays some thousands of cents to the HHI for every stream. So there's a lot of technology which is really delivered from Berlin to the world. But now back to the numbers. So the traffic between Berlin and rest of the world is around about 14 terabit per second. So this is an average communication amount. And if it's maximum, it's roughly double. So 28 terabit per second is possible. But 14 terabit per second is a long-term average of communication. And starting with these 14 terabit per second, what does it mean? This is the communication from Berlin to the rest of the world. But there is also another information available from all these data centers, and we visit them and talk to them and share now all these informations. Within one data center, most parts of the whole internet are stored. So every huge data center is a not complete, but a 90 to 95% copy of the internet to serve the users with data and not look for these data in US or China or somewhere else. No, the data centers normally look in their store and normally they find something. So if you look for very strange data in Malaysia, which no one before tried to find, it will take a little bit longer, maybe, because now the data really have to go from Malaysia over different nodes to your home device. But back, from the data centers, we have the information that the traffic inside of the data center is around about 10 times higher than to outside. So 90% of all the traffic is inside, between the racks, between the servers, between the CPUs inside. So some 140 terabit per second communication within all these data centers only in our region. And starting from this, I do a theoretical approach. First is there are some theoretical findings. How much energy do we need to run to have 1 bit, to transport it or to store it? So there's a theoretical minimum, means 1 electron stored with 1 point or 0.7 volt because of silicon. So this is an energy of around about 1.4 picojoule per bit. So this is a theoretical minimum for an electrical approach, for an electrical driven computer or communication link. And this means all this communication within all these data center, when they run pure electric, we can reduce the amount of energy consumption for the communication down to 44 terajoule per year. This is a lot, but if you go on the other side and do it completely optical, so the communication, the transport, and the storage of a bit, it just takes 4.4 femtojoule. This is a factor of 1,000 less than for electric storage. Then we can shrink down the energy consumption of all the data centers to something of a supermarket, something like this. But this is theoretically. We all know theory is, theory, we cannot reach it in a real world. And therefore, I also take these numbers and scale them up on a global scale, because I think the data centers in Berlin, they are not different from them in US or China or Japan or wherever. So the potential is the same. And the potential is the following. First, I take a global perfect world. So theory is feasible, it's possible, we do it. The real energy consumption of today for the whole internet is some 812 terawatt per hour. Terawatt hours. So you can remember this was the number we have given before. When we reduce everything in every computer and every storage and all the communication between them to the ideal theoretic minimum, we can reduce the whole energy consumption of the internet down to some 5 gigawatt hours. It's even huge, but you can see it's more than 100,000 less. And on an ideal world, when we do this all photonics, we can go down to 70 megawatt hours. So this is 1 million less or 100 million less. But theoretically, it's ideal and it's absolutely not realistic. It will never happen. But from this starting point, we can check what is possible, what could happen. And this is a scenario which is much more realistic. Again, we start with 800 terawatt hours for the whole internet. And if you use perfect electric driven machines, means in the lab we have right now single electron transistors for the computers, and we do everything which is possible, and it's really possible and shown in labs. Then we can go down to some 6 terawatt hours. So this is again a reduction of a factor of 100 from today. And then when we also do optical communication between the racks within the data center, within the CPUs, even on the main board, of course, but even within a CPU, when an AI processor is talking to his memory, it's right now ongoing that this communication, even it's done optically with optical links with some 2 millimeters. Then, and this is realistic, and there are first approaches on the even on the market to do this, we can go down to 3 terawatt hours. The last point, if you've done everything with optics, so even calculating with photons, so an all optical computer, not a quantum computer, but an all optical computer, we can shrink down this by a factor of 1000. But this last point, I'm not sure how realistic this is, that everyone is using an all optical computer at home, means all devices, all mobiles are just working with light inside, maybe for the next 100 years. But to shrink down the whole energy consumption to 3 terawatt hours, this is a realistic scenario, in my opinion, or in the opinion of my companies and data centers working on this. But it takes around about 30 to 40 years. And now, starting from this, when we think about that the data consumption will not decrease, it increases by 20% every year. This means in 40 years, we have a data consumption which is factor of 1,000 to 2,000 higher than today. And this at the end means, sorry to say, even in a realistic world with perfect optical communication as much as possible, we will have the same energy consumption than today, but with a bandwidth of some 2,000 more. And this is exactly what is working on. Right now, we run out of energy for all these data centers, so we have to do this. We have to shrink down the bandwidth, or we have to shrink down the energy consumption. And it's right now ongoing. And the data centers, they have to pay for, of course. So they're not on a green planet to save the planet, sorry to say, but it costs so much and energy is so expensive that they, from an economic view, they have to reduce the energy consumption of their data centers by amount of some 100, 200, something like this from today, to run the internet also the next years. And it's possible. We have the technology, and also part of this technology is right now entering the market, but it don't gives us the perspective that we run an internet which consumes so less energy that it doesn't matter anymore. We are so hungry on data that we have to shrink down the energy consumption per bit dramatically to fulfill this need on communication on data. Maybe when we also take this in account, that there is a technology to help, but not to help in any case. So reducing the amount of data we use will also help a lot. With AI, for one example, AI is a very powerful tool, but my suggestion is not to ask ChatGPT about first names or about the weather of today or something like this, because a simple Google question or Google request costs roughly 1,000 times less energy than an AI question. When I ask ChatGPT, we are in the region of some half of a kilowatt. And for a question on Google, we are in the region of half of a watt or something or less. So this is also something we can do. We can use AI, but we always have to think about, is it really needed to ask an AI, or can I ask a normal standard search engine? So with this, I hope I give a little overview about these energies and also the huge amounts. And maybe now you heard for the first time something about theta. So it's 1 with 21 zeros. But this also, on the other hand, means we have to do something, that we live on a green planet also for next generation and the generation after. They also want to communicate, I'm quite sure. And with this, I thank you very much for your attention, and I'm open for question and love to give answers.
Yeah, Adrian, thanks a lot for the presentation. Quite interesting, even though the outlook is maybe not as bright as we would like it, with the ever increasing energy hunger. So even if we are using the smartest technology, which obviously is optics and photonics, we're going to have a big problem supplying all that power. So we definitely need a plan for that, I guess. So one thing I really found interesting was when you said that in, I think, 2005 was the point where the power consumption of the internet did surpass the power consumption of lighting.
Yes.
And the interesting thing is that the power consumption of lighting since then has gone down a lot. So
no. This is something I mentioned when I was part of the research institute. We also do LEDs, and we bring a lot of LEDs in. With 2005, also this photonic revolution starts really on going on the market, that we exchange incandescent lamps and the classical bulbs by LEDs.
Mm-hmm.
But the energy consumption of lighting don't goes down with this, but the amount of lumens which are generated by this lighting goes up. And so with every bulb we installed with LEDs, so we save energy by a factor of 20 or something like this.
Mm-hmm.
But nowadays we install 20 times more light.
Okay, classic rebound effect.
Classical rebound effect. So the whole energy consumption of lighting, it's constant. It's a little bit decreasing. You're right. It's a little bit decreasing with the revolution of LEDs. And maybe we can have the same result with the internet, with the change in communication to optics and photonics. And also when we install photonics in the data centers itself, maybe we can have a little decrease in energy consumption, but a huge increase of data consumption itself. So maybe it's not a balance, maybe it's a decrease, maybe it's an increase. But as you mentioned, we have to do something. We have to take this in account, every one of us. So do we need all these huge amounts of data? Always? Do we need 4K? Do we need 8K high resolution streaming? And there are a lot of revolutions going on. But at the end, it's a very tricky balance if it decrease or increase.
Okay. So that means we are going to be able to do a lot more with what we're using, but we are not going to use less. So in the long run, we have to build the Dyson sphere, I think.
Yes, yes.
Yeah.
Good approach. Let's start.
You talked a bit about photonic computing.
Mhm.
So what is the state of the art right there? Are we close to seeing actual photonic AI, or is that still something that's off in the future?
Both. Right now on the market, there are some startups working on all optics computing, like also in Berlin, it's a company Architectonics. They show an all optical computer which runs with 20 NAND gutters. So you can calculate a little bit. You can do an 8-bit calculation. It's possible, but completely only with light. And this is a very interesting point. It's just an 8-bit multiplier or yeah, let's say multiplier. But he runs with some 400 gigahertz.
Oh, that's not bad.
That's not bad, exactly. And the potential is to go to 1 terabyte to 1 terahertz in calculating, and also to scale it up because it's an lithographic process. With a bigger processor, we can go to several of these multipliers and later on CPUs. But there are first multipliers, 8-bit multipliers running all optics on the market.
Mhm. Okay. And what is about the AI chip that's made by, I think it's QN, is the name of the company? Is that something that's close to getting to the market?
I'm not sure. It's very complicated because all of these AI companies, they pronounce a lot, they do marketing, and they sell the companies for billions and billions. And there was one point when I visited the Photonics West in January this year. There was a very interesting talk on a big stage. It was a big summit, so-called, photonic integrated circuit. And the keynote was held by someone who sells his company for 5 billion. So this was a hero, of course. And then he talked about what they plan. They plan an all optical data center, shrinking down the energy consumption, doing everything with photonics, even the communication between the chiplets inside of each CPU. They want to do optics. And so they have a whole setup from data center itself, so from concrete down to chiplets, everything within one company. This was the idea, and he sold this idea for 5 billion. And at the end of the talk, he said, yes, well, when we have our first customer, we will buy all available VCSEL lasers on planet. Okay, sounds great. But in my head, it runs and then it clicks. Okay, first you sell your company for 5 billion without any customer and without an available solution. You cannot deliver. You cannot buy all the VCSEL lasers from this planet. So you cannot deliver and you have no customer. And you get 5 billion for this only idea.
What can go wrong?
That's America. Yes, and so I don't believe in all these press releases.
Yeah.
It's just marketing. I believe when I see something in the lab, I believe it.
Mm. Yeah.
So quantum computer, I do believe. I saw quantum computer. I run a quantum computer. I believe that they are there. But an all optical AI coprocessor, something like this, I don't believe.
So that still remains science fiction. But yeah, we'll
But
see.
it's close to. It's possible. It's possible. But
Yeah.
now we have to do this. Yeah.
Yeah. So, any questions from the audience? As I said, when you don't want to speak, just type it into the chat, and we are going to try to answer the questions. I think it's always interesting to see how technology develops. I mean, I'm old enough to have seen the early personal computers, the personal computer revolution, as it was called. And back then, many people didn't believe that they would make any significant impact into the market or into the way we work and stuff like that. And then all of a sudden they did. And
Yes.
looking back, it was one of the most impactful technologies that was ever developed. And with the internet, it did get an additional boost. And after all, it changed society, how the whole society works.
Yes.
So I would always recommend to never underestimate possible consequences from new technology, and it's always a good idea to keep an eye on what's developing.
Exactly. Yep. You're right.
Okay, then let's wrap up for today. Thank you very much again for your presentation. It was really interesting. And if you're watching this video on YouTube, don't forget to like and subscribe. The working group for energy policy of the German Pirate Party does this type of events in a loose fashion. We do that a couple times a year whenever we can find somebody who has an interesting topic to talk about. So visit our channel, and there will be more soon. And thank you, and bye-bye.